There is a bear walking across the Arctic sea ice right now in temperatures that have fallen so far below zero that the moisture in a breath freezes before it reaches the ground, in darkness that has lasted for months, on a surface that is itself floating on an ocean that could swallow the bear in seconds if it cracked beneath its feet. And the bear is not struggling. It is not huddled against the cold or searching desperately for warmth. It is moving with the calm, unhurried confidence of an animal that has been shaped by millions of years of selection into the most perfectly cold-adapted large predator on Earth. An animal whose every feature, from the hollow structure of its fur to the chemistry of its blood, from the insulating architecture of its paws to the extraordinary metabolic flexibility of a pregnant female sleeping through winter, has been refined to not merely endure the Arctic, but to thrive in it completely. Tonight we will follow the polar bear gently from the surface of the sea ice where it hunts, into the biology of the body that makes the hunt possible, through the long sleep of winter and the extraordinary birth that happens inside it, and out into the questions that the bear's future in a warming world now quietly raises. So let the warmth of this room wrap around you like a second skin. Let the cold stay where it belongs, far outside and far away, and drift with me onto the ice, where the white bear is already moving through the dark with the certainty of an animal that has never needed to be afraid of winter. The polar bear's fur is one of the most written about biological structures in popular science, partly because it performs so extraordinarily well, and partly because one of the most frequently repeated facts about it turns out to be more complicated than it first appeared. For decades, it was stated with confidence that polar bear hairs are hollow, transparent tubes that act like fiber optic cables, conducting ultraviolet light down to the dark skin beneath and converting it into heat. This description appeared in textbooks, nature documentaries, and popular articles with the confident tone of established fact. When researchers tested it rigorously in the 1990s, they found that the fiber optic mechanism does not actually work in the way described. Polar bear hairs do not efficiently conduct UV light to the skin, and the heat contribution of this supposed mechanism is negligible. But in correcting the myth, the researchers discovered something more interesting. The actual mechanisms by which polar bear fur insulates are themselves remarkable enough to need no embellishment. Each individual polar bear guard hair is indeed hollow, containing a core of air, rather than the solid keratin that fills the hair shaft of most mammals. This hollow core reduces the hair's thermal conductivity, making it a better insulator than a solid hair of equivalent diameter would be. But the primary insulating value of the guard hair coat comes not from the hollow cores, but from the air trapped between the hairs themselves, which form a dense interleaved layer that resists wind penetration and traps a still warm boundary layer of air against the skin surface. The guard hairs are also coated with an oily, water-repellent surface layer that sheds water during swimming and prevents the coat from becoming waterlogged in the way that a less hydrophobic fur would. When a polar bear emerges from the Arctic Ocean after a swim, a vigorous shake removes most of the surface water, and the guard hair's water-repellent properties allow the remaining moisture to drain away quickly rather than being retained in the coat where it would conduct heat away from the skin. Beneath the guard hair layer lies a dense underfur of shorter, softer hairs that provides the primary insulating medium for the bear's body. This underfur layer traps still air in a deep, lofted structure, similar in principle to the down of an Arctic breeding bird. And it is the combination of this underfur layer with the wind-resistant outer guard hairs that gives the polar bear its remarkable cold tolerance. The underfur is so effective that the polar bear's primary thermoregulatory challenge in cold conditions is not staying warm, but avoiding overheating during activity, particularly during the vigorous exertion of running or swimming. Polar bears overheat relatively easily when they move quickly, which is one of the reasons they generally prefer a slow, energy-conserving pace even when covering long distances on the ice. The insulation system that protects them from the Arctic cold becomes a liability the moment the metabolic heat of exertion exceeds the rate at which that heat can be lost to the environment. The color of polar bear fur is another aspect that holds more complexity than casual observation suggests. The fur appears white to human eyes, providing what seems like obvious camouflage against the snow and ice of the Arctic environment. But the individual hairs are not white in the sense of being filled with white pigment. They are actually colorless, and the white appearance is an optical effect produced by the scattering of all wavelengths of visible light from the numerous air-keratin interfaces within and between the hollow, translucent hairs. The same physics that makes snow appear white and that makes the foam on a wave white, despite being made of transparent water, makes polar bear fur appear white despite the absence of any white pigment. The skin beneath the fur, by contrast, is deeply black, and the black skin is visible on the bear's nose and the bare skin around the eyes and mouth. This black skin absorbs solar radiation efficiently and contributes to warming the blood in the superficial vessels of the face, one of the few areas where the insulation layer is thin enough for meaningful heat absorption from sunlight. The thermal insulation of the fur also interacts with the bear's body shape in ways that reflect broad principles of heat conservation in cold environments. The polar bear has relatively small ears for its body size, reducing the surface area of a poorly insulated appendage that would otherwise be a significant site of heat loss. The muzzle is proportionally shorter than that of brown bears, the polar bear's closest living relative, again reducing the surface area of a region with limited insulation. The overall body shape is more compact than a brown bear's, with a higher ratio of volume to surface area, which minimizes the rate of heat loss per unit of metabolic heat produced. These are the same geometric principles that explain why Arctic animals generally have shorter, rounder proportions than their tropical relatives, a pattern known as Allen's rule, and in the polar bear, they are expressed across multiple anatomical features simultaneously, each one a small increment of heat conservation that adds up across the whole body to a significant advantage in the energy budget. The molecular biology of polar bear fur has attracted research attention in recent years, as genomic tools have made it possible to examine the genetic differences between polar bears and their brown bear relatives at the level of individual gene variants. Studies comparing the genomes of the two species have identified polar bear-specific variants in genes associated with fur development, pigmentation, and the structural proteins of hair that are likely related to the specific properties of polar bear fur. These genetic differences are relatively recent in evolutionary terms, having accumulated over the 3 to 5 million years since the polar bear lineage diverged from brown bears, which is a remarkably short time for such extensive cold-adapted specialization to develop. The speed of this evolutionary change suggests that the selective pressure for cold adaptation in the ancestral polar bear population was intense, driving rapid fixation of beneficial variants across multiple gene systems simultaneously. The polar bear's relationship with fat is central to nearly everything it does, and understanding this relationship is essential to understanding how the bear manages the physiological demands of life in the Arctic. A large adult male polar bear in good condition carries a blubber layer up to 11 centimeters thick beneath the skin, supplementing the insulating function of the fur with a second layer of thermal resistance built into the body itself. This blubber is not simply passive insulation, it is the bear's primary energy reserve, the fuel that sustains it through periods when food is unavailable, the substrate from which a denning female synthesizes the milk to feed her cubs, and the caloric bank against which the unpredictable timing of hunting success is balanced. A polar bear's body is, in a very real metabolic sense, a fat management system, accumulating fat when prey is available and drawing on it systematically when prey is not. The primary prey of polar bears is the ringed seal, and the way polar bears hunt seals reflects a patience and sensory acuity that is all the more impressive for the featureless, wind-scoured environment in which it is deployed. The most important hunting technique is called still hunting, a method in which the bear locates a seal's breathing hole in the sea ice, crouches motionless beside it, sometimes for hours, and waits for the seal to surface to breathe. Ringed seals maintain multiple breathing holes in the sea ice above their feeding areas, returning to each hole periodically through the day and night. The polar bear, with its extraordinary sense of smell, can detect the faint scent of a seal's breath escaping from a hole through up to 1 meter of snow, locating the hole even when it is completely concealed by wind-drifted snow. Once the bear has found the hole and settled beside it, the hunt becomes a test of stillness, with the bear remaining motionless and silent for however long it takes for the seal to choose that particular hole on that particular surface visit. The olfactory capability of the polar bear is among the most sensitive documented for any land mammal, and it is the sensory foundation on which the entire hunting system rests. Polar bears can detect the scent of a seal's breathing hole from up to 1 kilometer away under favorable wind conditions, and they can smell a seal pup in its birth lair beneath a snowdrift from a distance and through the covering of snow and ice. The neural infrastructure supporting this olfactory capability occupies a proportionally large area of the polar bear's brain, reflecting the evolutionary premium placed on smell-based prey detection in an environment where visual information is often limited by darkness, blizzard conditions, or the featureless uniformity of the ice surface. The bear essentially reads the Arctic landscape through its nose, building a map of seal activity, sea ice quality, and other environmentally relevant information from the chemical signatures carried in the wind. When a seal surfaces at the breathing hole, the polar bear's strike is extremely fast, reaching down through the hole with a forepaw or plunging the head directly into the opening to seize the seal with its jaws. The force of the strike can break through ice as thick as several centimeters if the seal surfaces near a thin spot, and the power available from the massive forelimbs and shoulders of a large male bear is sufficient to haul a ringed seal, which weighs up to 70 kilograms, directly out of the water onto the ice surface in a single motion. The mechanical efficiency of this technique, which converts the energy of a single explosive muscular contraction into prey capture, reflects a hunting apparatus calibrated to the specific geometry of the breathing hole hunt over hundreds of thousands of years of interaction between polar bears and ringed seals. The seal has evolved multiple breathing holes and a continuous monitoring of the surface sounds above them, partly in response to this predation pressure. The bear has refined its stillness and its strike in response to the seal's vigilance. The two species have shaped each other in a predator-prey evolutionary dialogue conducted on the ice. The caloric content of a ringed seal is substantial, and the specific parts of the seal that the polar bear preferentially consumes reflect the bear's metabolic priorities. Polar bears are highly selective eaters when prey is available, focusing on the blubber and skin of the seal and leaving much of the muscle meat, which human hunters and other scavengers, including Arctic foxes, subsequently consume. This selectivity is metabolically rational. The blubber provides caloric density and fat that is directly usable for the bear's own blubber and energy reserves, while the lean muscle meat, though nutritious, contributes protein that the bear's metabolism must convert at some energetic cost. When food is abundant, the bear maximizes the efficiency of its caloric intake by eating selectively. When food is scarce, it consumes the full carcass, prioritizing caloric intake over metabolic efficiency. The relationship between seal availability and sea ice extent is the central ecological link in the polar bear's existence, because ringed seals use sea ice as a platform for resting, pupping, and surfacing to breathe. In areas where sea ice is absent, ringed seal density is low, and polar bears in those areas cannot feed effectively. The seasonal availability of sea ice therefore determines the temporal structure of the polar bear's feeding opportunities, with most of the year's caloric intake accumulated during the sea ice season and the ice-free summer months representing a period of enforced fasting for bears in most populations. How long this fasting period lasts, how much fat the bear accumulated before the ice retreated, and how efficiently the bear manages its reserves during the fast together determine whether the bear enters the next sea ice season in sufficient condition to resume effective hunting. In a warming Arctic where sea ice extent is declining and the ice-free season is lengthening, this seasonal energy budget is under increasing pressure in ways that the bear's extraordinary fat management system cannot indefinitely compensate for. The polar bear is classified as a marine mammal, a designation it shares with seals, walruses, and cetaceans, and that reflects the degree to which its existence depends on the ocean environment rather than the terrestrial one. The sea ice on which the bear hunts is floating ocean, and the bear's ability to swim across open water between ice flows or to land areas is a fundamental part of its ecological mobility. Polar bears are capable swimmers, using a dog paddle stroke with their large, partially webbed forepaws to propel themselves through Arctic waters, with their rear paws trailing as rudders. They have been recorded swimming distances of more than 680 kilometers continuously in a single open water crossing, a feat documented from satellite-tagged bears in the Beaufort Sea, and representing a physiological endurance performance that few large terrestrial mammals could approach. The paws of the polar bear are a study in multifunctional adaptation. Each forepaw can be up to 30 centimeters across, roughly the diameter of a dinner plate, and the size serves several functions simultaneously. On snow and ice, the large surface area distributes the bear's weight across a wider footprint, reducing the pressure per unit area and decreasing the risk of breaking through thin ice. The paw pads are covered with small, soft papillae, tiny bumps that increase friction against slippery ice surfaces in the same way that tread patterns on a tire increase traction on wet roads. These papillae interdigitate with the surface irregularities of ice at a microscopic scale, providing grip that allows the bear to walk confidently on surfaces that would be treacherous for any animal with smooth-soled feet. The fur between the toe pads provides additional insulation and prevents the pads from freezing to ice in the way that bear skin would in extreme cold. The swimming capability of the polar bear requires a specific physiological profile that differs from what would be optimal for a purely terrestrial predator. The enormous fat reserves that provide metabolic fuel during fasting also contribute to buoyancy in the water, making swimming less energetically demanding than it would be for a leaner animal. The dense, water-repellent fur coat maintains its insulating properties even when wet, preventing the catastrophic heat loss that would occur if Arctic water were in direct contact with the skin's surface. The large forepaws that are so effective at providing traction on ice are also efficient paddles in water, their size generating substantial propulsive force with each stroke. The same anatomy that makes the polar bear effective on ice makes it an able swimmer, a convergence of function that reflects the continuity between ice and water as habitat elements in the bear's real ecological world, where the boundary between solid ice and liquid ocean is neither permanent nor sharp. Long-distance swimming has become more common for polar bears in some populations as sea ice extent has decreased and the open water distances that bears must cross to reach ice have increased. The Beaufort Sea satellite tracking study that documented individual bears swimming hundreds of kilometers found that some of these long swims resulted in measurable weight loss and, in some cases, cub mortality when mothers with young cubs attempted the crossings. The physiological cost of long sustained swimming in cold water, even with the bear's excellent thermal insulation and fat reserves, is substantial, and swims that would have been unnecessary or much shorter when sea ice extent was greater now represent significant energetic challenges for bears attempting to maintain access to their hunting grounds. The swimming ability that was an occasional supplement to ice travel is becoming a more frequently required capability, and the energetic costs are accumulating in population-level fitness data. The nose of the polar bear, which we have already discussed as the primary prey detection instrument, is also a critical tool for navigation across the sea ice and open water environment. Polar bears navigate using a combination of celestial cues, which are available during the polar summer but absent during the polar night, and olfactory and possibly magnetic cues that can function in the continuous darkness of winter. The bear's ability to return to specific areas, to locate polynyas, open water areas in the ice where seals concentrate, and to find productive hunting areas across a range that in some populations spans hundreds of thousands of square kilometers implies a navigational capability that goes beyond simple landmark recognition. Some researchers believe that polar bears may use the Earth's magnetic field as a compass, a capability documented in several other mammals, though direct evidence for magnetoreception in polar bears remains limited. What is clear from tracking data is that the bears cover their enormous ranges with a directional consistency that implies reliable long-distance navigation regardless of the specific mechanisms involved. One aspect of polar bear paw anatomy that has attracted recent biomechanical interest is the relationship between paw size, body weight, and ice load bearing. The ice conditions that polar bears navigate are highly variable, from thick multi-year ice that can support a vehicle to thin first-year ice that might be only centimeters thick over open water. The bear's ability to assess ice thickness and adjust its behavior accordingly, spreading its weight by lying flat, when crossing thin ice or redistributing its load across a larger footprint, suggests a real-time awareness of ice mechanical properties that goes beyond instinctive movement patterns. Young bears learn ice assessment behaviors in part through observation of their mothers, and bears that survive long in ice-variable environments show behavioral flexibility in ice navigation that has the quality of accumulated experience. The ice is not a stable platform, but a constantly changing, mechanically variable surface, and the bear that navigates it successfully does so with a combination of anatomical equipment and learned behavioral judgment that is still being appreciated in its full complexity. Of all the extraordinary biological events in the polar bear's life history, the one that most captures the imagination is what happens inside the maternity den during the Arctic winter. A pregnant female polar bear, having accumulated massive fat reserves during the summer and autumn feeding season, excavates a den in a deep snowdrift sometime in October or November and seals herself inside. Over the following months, in complete darkness, in a snow-insulated chamber barely large enough to turn around in temperatures well below the freezing point outside the den, though modestly warmer inside due to the insulating properties of packed snow and the female's own body heat, she gives birth to cubs that are among the smallest and most undeveloped newborns of any large mammal, and she nurses them through their most vulnerable early weeks on milk produced entirely from her own body reserves, without eating, without drinking, and without leaving the den. The physiological state that the female polar bear maintains throughout the denning period is a subject of considerable scientific interest because it differs in important ways from true hibernation as exhibited by species like ground squirrels. True hibernators drop their body temperature dramatically, sometimes to near freezing, and enter a state of profound metabolic suppression in which heart rate and breathing rate decrease by more than 90%. The denning polar bear does not drop her core body temperature significantly. Her metabolic rate decreases by approximately 50 to 75% compared to her active summer rate, but her body temperature remains within a few degrees of normal. This state, sometimes called carnivore lethargy or walking hibernation in the scientific literature, is metabolically distinct from the deep hibernation of true hibernators and from the normal sleep of non-hibernating mammals, occupying a physiological middle ground whose precise hormonal and metabolic regulation researchers are still working to fully characterize. The cubs born in the maternity den are born after a gestation period of approximately 8 months, but this figure is somewhat misleading because it includes a period of delayed implantation that is characteristic of the bear family. Fertilization occurs in spring, but the embryo develops to the blastocyst stage and then halts further development, floating free in the uterus without implanting in the uterine wall. Implantation and the resumption of embryonic development occur in autumn when the female has accumulated sufficient fat reserves to support the pregnancy and subsequent denning. This delay is an adaptation that decouples the timing of mating, which is constrained by the seasonal aggregation of bears on the sea ice, from the timing of birth, which must occur in the protected environment of the winter den. Without delayed implantation, the fixed gestation length would make it impossible to mate in spring and give birth in the den in midwinter. Newborn polar bear cubs are remarkably altricial, born blind, toothless, and covered with fine, sparse fur that provides almost no thermal insulation. Weighing approximately 600 grams, roughly the weight of a large apple. This tiny, helpless neonate is born to the largest land predator in the Arctic, a mother who may herself weigh 200 kilograms or more. The disproportion between mother and offspring size at birth is extreme by the standards of large mammals, and it reflects the metabolic constraints of the denning fast. Producing small, undeveloped offspring costs relatively little in terms of the mother's reserves at birth, deferring the major metabolic investment to the postnatal nursing period when the mother is still in the den and the cubs are growing rapidly. The mother's milk, which has a fat content of approximately 31%, far higher than the milk of most terrestrial mammals, drives a growth rate in the cubs that takes them from 600 grams at birth to approximately 10 kilograms by the time the den is vacated in March or April, a more than 15-fold increase in body mass in approximately 3 months. The thermoregulation of newborn cubs in the den is entirely dependent on the mother, who keeps them pressed against her body and enclosed within her fur throughout the early weeks of their development. The cubs cannot generate sufficient metabolic heat to maintain their body temperature independently until they have grown large enough and developed enough fur to do so, which takes several weeks after birth. During this period, the mother's body is simultaneously an incubator, a food source, and a shelter, providing the controlled thermal and nutritional environment that the cub's undeveloped physiology cannot yet sustain independently. The intimacy and intensity of the bond between mother and cubs in the den, conducted in darkness and silence over months of shared warmth, is thought to contribute to the strong mother-offspring bond that persists after den emergence and underlies the extended period of maternal teaching that characterizes polar bear cub development. When the den is finally vacated, typically in March or April when the Arctic light is returning and the sea ice is still extensive enough to support hunting, the mother emerges, having lost between 150 to 200 kilograms of body mass during the denning fast. She has been without food for 5 to 7 months, has nursed 2 or sometimes 3 cubs through their most vulnerable developmental period, and has maintained a near normal body temperature throughout. The cubs that emerge with her are healthy, vigorous, and curious, their development driven by the extraordinary nutritional investment their mother has made from her own body. And the mother, despite her depleted condition, immediately begins moving toward the sea ice and her first hunting opportunities in months, driven by the nutritional urgency of a body that has been drawing down its reserves for the better part of a year. The maternal bond that carried the family through the den now transitions into the active teaching relationship of the sea ice, where the cubs will spend the next 2 years learning from their mother everything they need to know to survive as polar bears. The sea ice of the Arctic is not a single uniform surface. It is a complex, constantly changing mosaic of ice types, thicknesses, ages, and structural conditions, each with different mechanical properties and different implications for the bear's hunting opportunities. First-year ice, which forms in autumn from the freezing of open ocean water, is typically thinner and more fragile than multi-year ice, which has survived at least one summer melt season and consolidated into denser, more stable structures. Pressure ridges form where ice flows collide and buckle upward, creating irregular topography that can provide wind shelter and denning sites, but also complicates travel. Leads, long narrow channels of open water that form when ice flows separate under wind or current stress, are hunting hotspots where seals must surface frequently, but they also represent barriers to travel and hazards for bears that fall through thin ice at their edges. Polynyas, larger persistent areas of open water maintained by wind patterns or upwelling currents, are ecologically critical zones where seal density is highest, and polar bears that know the locations of reliable polynyas in their ranges have a significant advantage over those that do not. The polar bear navigates this complex, dynamic ice environment with what appears to be a detailed learned knowledge of the sea ice conditions in its home range, accumulated over years of experience and supplemented by the sensory information the bear continuously extracts from the ice surface underfoot. Bears test ice before committing their full weight to a suspect surface, placing a forepaw or pressing with the nose to assess thickness and integrity before crossing. They read the visual and acoustic properties of ice at a glance, distinguishing the blue-green clarity of solid, thick ice from the milky whiteness of thinner first-year ice, and listening for the specific sounds that ice makes when it is stressed or close to the point of breaking. This ice-reading competence is learned rather than instinctive, with young bears accompanying their mothers and observing her ice assessment behaviors across 2 years of apprenticeship before becoming independent. The hunting productivity of different ice types varies in ways that directly affect the bear's energy budget. In areas of stable, extensive sea ice with good ringed seal populations, a skilled polar bear in prime condition can accumulate substantial fat reserves during the hunting season. In areas of unstable or fragmented ice, where seals are less abundant or harder to access, hunting success is lower and the seasonal fat accumulation is correspondingly reduced. Tracking studies that combine location data from satellite tags with measures of ice conditions have shown that individual bears make habitat choices that favor sea ice conditions associated with higher hunting success, using prior experience of productive areas to guide their seasonal movements. The bears are not simply following ice wherever it forms. They are navigating towards specific ice conditions that their experience has associated with productive hunting, a pattern of spatially informed decision-making that implies a learned, experience-based knowledge of their environment. The polar bear's interaction with the sea ice also includes a dimension that researchers have only recently appreciated in full. The bear's use of sea ice as a travel medium that connects its hunting grounds, its denning areas, its mating locations, and its resting sites across a range that in some populations covers hundreds of thousands of square kilometers. The sea ice is not just a hunting platform. It is the roads, the bridges, and the landscape of the polar bear's world, and the connectivity it provides between habitat patches is essential to the species' ability to access the full range of resources it needs across the annual cycle. When sea ice extent decreases, this connectivity is disrupted. Hunting grounds that were accessible from denning areas become separated by open water. Productive polynyas that were reliably within a bear's seasonal range become inaccessible. The fragmentation of the sea ice habitat is not just a reduction in the total area available, but a disruption of the spatial connectivity that allows the bear to function as an integrated ecological unit across its full home range. The sensory world of the polar bear on the sea ice extends beyond smell and vision and touch to include hearing, which plays a role that is sometimes underappreciated. The specific sounds of seals, both their vocalizations under the ice and the sounds of their movement in breathing holes, can alert a bear to the presence of prey at distances of hundreds of meters, particularly in the relative acoustic quiet of the polar winter. Bears have been observed stopping and tilting their heads in a listening posture at distances from potential seal locations that are consistent with acoustic detection, and they will approach the direction of detected sounds with a directional precision, suggesting that they have localized the sound source effectively. The integration of olfactory detection at long range with acoustic cues at intermediate range and visual confirmation at close range gives the polar bear a multi-sensory prey detection system that is effective across a wide range of visibility and weather conditions, from clear, calm days to blizzard conditions that reduce visibility to meters and make visual hunting essentially impossible. The ice the polar bear walks on is also an acoustic environment that the bear reads passively as it travels. The sounds of ice stress, the deep groans and sharp cracks of ice being compressed or stretched by thermal contraction, or the pressure of wind and current, provide information about the mechanical state of the ice ahead. A bear that hears the specific sounds of ice about to fail under pressure adjusts its route accordingly, responding to acoustic information that a less attentive traveler would miss. Whether this ice acoustic awareness is a learned capability or reflects an innate sensitivity to ice sounds that are ecologically relevant across the bear's range is not fully established, but its practical effect is clear from behavioral observations of bears adjusting their travel routes in response to ice sounds in ways that are well ahead of visible ice deterioration. The polar bear's navigation of its ice world is, in this sense, a continuous sensory reading of an environment that is constantly telling the bear something about itself. The polar bear summer is defined by the absence of what makes everything else possible. As Arctic temperatures rise from spring into summer, the sea ice retreats from the coastal areas of the polar bear's range, often retreating entirely from some regions for weeks to months before reforming in autumn. During this ice-free period, the bears that depend on sea ice hunting are forced ashore, where they can no longer hunt seals effectively and must survive primarily on their accumulated fat reserves, supplementing with whatever terrestrial food sources are available: berries, bird eggs, grasses, carrion, and occasionally terrestrial mammals that are far less calorie-dense per unit of hunting effort than ringed seals. This terrestrial period is, in metabolic terms, a fasting period punctuated by occasional low-quality foraging, and its duration directly determines how much of the fat accumulated during the hunting season will be depleted before the bears can return to the ice in autumn. The metabolic state of a fasting polar bear in summer is a physiological achievement in its own right. Rather than simply burning through fat reserves at the rate required to maintain all normal physiological functions, the bear shifts into a state that researchers have called walking hibernation, in which metabolic processes are reorganized to extend the usable period of the fast as long as possible. Metabolic rate decreases. Nitrogen recycling pathways that normally result in urea excretion shift toward recycling nitrogen back into protein synthesis, slowing the loss of lean muscle mass that would otherwise accompany an extended fast. The kidneys reduce urine production dramatically, conserving water in an environment where drinking opportunities may be limited. Researchers who have studied polar bear blood chemistry during the summer fast have found metabolic profiles that are distinct from both the active state and the denning state, representing a third physiological mode that sits between them and that helps the bear navigate the summer on the ice-free coastal environment without physiological deterioration that would compromise its ability to hunt effectively when the ice returns. The specific behaviors of bears during the summer onshore period vary considerably between populations and individuals, and some of the variation reflects learned adaptations to local food availability. Hudson Bay bears in northern Canada are well studied during their summer shore period, and researchers have documented these bears using a range of terrestrial food sources including crowberries, kelp, bird eggs from nesting colonies, and occasionally caribou and beluga whales in areas where these encounters are possible. Some individuals have learned to exploit specific local food sources, visiting berry patches at peak ripeness or positioning themselves at coastal sites where beluga whales regularly congregate at predictable seasons. These learned, individually variable foraging strategies represent the bear's attempts to manage their caloric balance during a period when the primary food source is unavailable, and their effectiveness directly affects the body condition with which individual bears enter the next sea ice hunting season. The interaction between polar bears and humans during the summer onshore period has been a source of both conflict and scientific opportunity across the communities of the Arctic where bears come ashore near human settlements. The town of Churchill in northern Manitoba, Canada, is the most widely known example, where hundreds of bears congregate on the western shore of Hudson Bay, waiting for the ice to form in November, and where their presence in proximity to a human town has created an unusual and extensively studied human-bear interface. The Churchill bears have been the subjects of decades of research, providing some of the most detailed long-term population data available for any polar bear subpopulation, including measurements of body condition, reproductive success, and phenological timing that have documented the effects of sea ice changes on bear welfare, with a resolution not available for more remote populations. The data from Churchill have been among the most influential in demonstrating that the shortening of the sea ice season in that population is associated with measurable declines in adult body weight, cub survival, and reproductive rates over the past several decades. The psychological and behavioral effects of the forced summer fast are not trivial. Polar bears are clearly animals capable of boredom, frustration, and what observers describe as restlessness during the onshore period, behaviors that are less obvious in the context of active sea ice hunting, but that become apparent when bears are confined to a terrestrial environment that offers little of what their ecology is built around. Bears play. They spar with each other in what appears to be socially facilitated activity that passes time and maintains social bonds. They rest extensively, lying flat on tundra or gravel beaches in the postures of maximum heat loss, attempting to remain cool in temperatures that are well below freezing by most human standards, but that the bear's excellent insulation renders uncomfortably warm for sustained activity. And they wait, with a patience that reflects the reliability of the ice's return built into them over thousands of years, for the temperature to drop and the freeze to begin, and the ice to carry them back to the water and the seals and the life they are built for. Polar bears are largely solitary hunters, and their social interactions are fewer and less complex than those of the intensely social species we have discussed in other parts of this series. But to describe polar bears as simply solitary would be to miss a social dimension that is real, though less visible than the matriarchal cultures of sperm whales or the huddle dynamics of emperor penguins. Polar bears communicate with each other through a combination of body posture, facial expression, vocalizations, and olfactory signals, and the sophistication of this communication system reflects the social challenges of an animal that must manage its encounters with conspecifics carefully in an environment where both cooperation and conflict have significant energetic stakes. The most elaborated social relationship in polar bear life is the mother-cub bond, which persists for 2 to 2.5 years after den emergence, and during which the mother provides not just protection and food access, but active behavioral teaching of the skills the cub will need for independent survival. Cubs learn hunting technique by observing their mothers, sometimes attempting to participate in hunts in ways that alert the seal, but that constitute practice for later competence. They learn ice assessment, swimming, and den site selection through experiences shared with and facilitated by the mother. They learn the geography of their home range through the travels the mother undertakes and the decisions she makes about where to go and when. The mother-cub pair is the fundamental unit of polar bear social structure, and the quality of the mother as a teacher and forager has direct, measurable consequences for the survival and reproductive success of her cubs in their first years of independence. Between adults, polar bear social interactions are largely dyadic, occurring between two individuals in the context of competition for resources, mating opportunities, or the negotiation of personal space on a shared resource like a seal carcass. Dominance relationships between males determine access to females during the breeding season and to food resources when multiple bears encounter the same prey simultaneously. These relationships are communicated and maintained through a rich repertoire of postural signals, including the classic bluff charge, the head-down threat posture, and the broadside display that presents the full body profile and maximum apparent size to a competitor. Physical fights between adult males, though they do occur, are costly and risky, and are generally preceded by extended periods of posturing, vocalizing, and mutual assessment, during which both animals evaluate whether the contest is worth the cost. Most encounters between adult males are resolved without serious physical contact through the signals exchanged in the assessment phase. The breeding aggregations that form on the sea ice in April and May, when sexually receptive females attract males from wide areas through olfactory advertising, represent the most complex multi-individual social situations in the polar bear's life. A female in estrus leaves chemical signals in her footprints and in other scent deposits that males follow across the ice from distances of many kilometers. Multiple males may track the same female simultaneously, leading to male-male competition that involves both the postural communication of dominance assessment and occasional physical combat. Females exercise some choice in their mating partners, and the length of the mating association, which can last a week or more, reflects a period of mate evaluation, as well as the multiple matings needed to ensure fertilization. The physiology of induced ovulation in polar bears, in which ovulation is triggered by the act of mating rather than occurring on a fixed cycle, makes the timing and duration of the mating association directly relevant to reproductive success. One of the more interesting recently documented social behaviors in polar bears is what some researchers describe as play behavior between adults, particularly between subadult males during the summer onshore period. Young males in their first years of independence have been observed engaging in extended reciprocal wrestling and mock combat play that looks quite different from the serious competitive interactions of fully adult males. These play bouts, which can last for hours and involve elaborate mutual signaling of non-threatening intent through open-mouthed displays and specific postural signals, are thought to serve a social bonding and skill practice function, allowing young males to develop combat skills in a relatively low-cost context and possibly to form loose associations with familiar individuals that persist across subsequent encounters. Whether these associations have any fitness consequences beyond the immediate skill development value has not been established, but their occurrence demonstrates that polar bears have a social behavioral repertoire that extends beyond simple competitive encounters and pair bond formation. The conservation status of polar bears sits at one of the more contested and scientifically complex intersections of wildlife biology, climate science, and political debate that exists in the natural world. The species is listed as vulnerable on the IUCN Red List, reflecting a population assessment that identifies ongoing and projected decline driven primarily by sea ice loss in a warming Arctic. The global population is estimated at somewhere between 20,000 and 31,000 individuals across 19 recognized subpopulations, a range of uncertainty that reflects both the genuine difficulty of conducting population surveys across the remote and vast territories these bears occupy, and the methodological differences between the survey approaches used in different regions. Some subpopulations are considered to be declining based on recent survey data. Others are considered stable or even increasing in some assessments. The heterogeneity in population trends across the species range reflects real variation in the rate and magnitude of sea ice change in different Arctic regions, as well as the different hunting pressures and management histories of bears in different countries. The relationship between sea ice decline and polar bear population trends is not simple or uniform, and understanding it requires distinguishing between effects operating on different timescales. In the short term, individual bears respond to reduced sea ice by spending more time ashore, reducing their caloric intake, and drawing more heavily on their fat reserves. These individual-level effects are measurable through body condition indices and are clearly occurring in some populations. In the medium term, declining body condition translates into reduced reproductive success, lower cub survival, and higher adult mortality, producing population declines that become detectable in survey data over years to decades. In the long term, if sea ice loss continues at the rate projected under high-emission scenarios, large parts of the polar bear's current range may become functionally unsuitable for the species because the sea ice season will be too short to support adequate hunting. The timescales on which these different effects operate mean that the full demographic impact of current sea ice losses will not be reflected in population data for years or decades, creating a gap between what the bears are currently experiencing and what the population counts currently show. The polar bear has become a symbol of climate change consequences in a way that carries both scientific validity and political complexity. As a large, charismatic, easily recognizable animal, whose habitat is directly and measurably affected by the primary driver of climate change, the polar bear represents the consequences of global warming in a form that is emotionally accessible in a way that abstract temperature or sea ice area statistics are not. This symbolic status has been both valuable and complicated for conservation science. Valuable because it has elevated public and policy awareness of Arctic ecosystem change. Complicated because it has made polar bear science a political flashpoint in which the natural scientific uncertainties inherent in population assessment have sometimes been distorted in both directions, with some sources minimizing evidence of decline and others overstating the certainty of projections. The actual scientific picture is nuanced, acknowledging both the real and measurable ongoing impacts and the genuine uncertainties in how individual populations will respond to projected future changes. What is not in scientific dispute is the trajectory of the Arctic sea ice system that the polar bear depends on. September sea ice extent, The late summer minimum that reflects the cumulative melt of the season has declined by approximately 13% per decade since satellite records began in the late 1970s, and the trend is accelerating. The 9 lowest September sea ice extents in the satellite record have all occurred in the past 12 years. Climate models project continued sea ice loss under all emission scenarios, with the extent of that loss depending on the trajectory of global greenhouse gas emissions. Under high emission scenarios, the Arctic is projected to experience summers that are essentially sea ice free by the middle of the century. Under lower emission scenarios that involve significant emissions reductions, more sea ice is preserved for longer, potentially maintaining enough summer habitat to support viable polar bear populations in parts of their current range. The polar bear's future is, in this sense, directly and quantifiably connected to decisions about global energy systems being made now, which gives the bear's conservation a policy dimension that wildlife management alone cannot address. The management of polar bear hunting adds another layer to an already complex conservation picture. Legal hunting of polar bears occurs in Canada and in Greenland, where indigenous communities exercise hunting rights that have existed for centuries and that form part of the cultural and subsistence economy of communities living in proximity to the bears. The management of these harvests involves annual quota negotiations that attempt to balance harvest sustainability against the preferences of hunting communities, and the data on which sustainability assessments are based have been the subject of ongoing scientific scrutiny. In the context of populations that are declining due to habitat loss, the interaction between hunting mortality and sea ice-driven reproductive decline becomes a more critical management consideration than it was when populations were stable or growing. How to balance the legitimate interests of indigenous communities with the conservation needs of a vulnerable species in a changing environment is one of the more genuinely difficult challenges in Arctic wildlife management, and it does not have a resolution that satisfies all stakeholders. The polar bear carries within its genome a record of the evolutionary history that produced it, and that history is considerably more complex and interesting than the simple narrative of a brown bear that went north and turned white. Genomic studies conducted over the past decade and a half have examined the genetic relationship between polar bears and brown bears in detail, and the picture that has emerged is one of a dynamic, ongoing relationship between the two species that includes not just a shared ancestor, but repeated episodes of interbreeding that have exchanged genetic material between the lineages across the hundreds of thousands of years since their divergence. This history of hybridization has left traces in the genomes of both species, and some of the adaptations that make the polar bear so exquisitely cold-adapted appear to have arrived in the polar bear lineage through introgression of beneficial genetic variants from brown bear populations rather than through independent evolution. The timeline of polar bear divergence from brown bears has been the subject of some scientific revision as genomic data have improved. Earlier analyses based on mitochondrial DNA suggested a divergence time of roughly 150,000 years ago. More comprehensive genomic analyses that examine the full nuclear genome have pushed this estimate back to approximately 400,000 to 600,000 years ago, a substantially deeper divergence that implies the polar bear lineage is considerably older than previously thought. This older timeline is consistent with the known fossil record of polar bears, which includes specimens from the Pleistocene that already show the characteristic morphology of the modern species, and it aligns with a period of glacial history during which Arctic sea ice would have been extensive and the ecological opportunity for a sea ice specialized bear would have existed for a prolonged period. The polar bear, in this framing, is not a recently evolved novelty, but a lineage of considerable antiquity that has survived multiple glacial and interglacial cycles before the one we are currently driving. The specific genetic changes that underlie the polar bear's cold adaptations have been identified through comparative genomic analyses that compare polar bear gene sequences to those of brown bears and black bears, looking for variants that are fixed or at high frequency in polar bears but rare or absent in their relatives. These analyses have identified a relatively small number of genes showing signatures of strong positive selection in the polar bear lineage, and their functions illuminate the specific physiological challenges of Arctic living. Genes involved in fat metabolism and cardiovascular function show particularly strong signals of selection, reflecting the demands of a diet extremely high in fat and the cardiovascular stress of managing this diet without the atherosclerosis that would afflict a human or most other mammals eating similarly. The polar bear has evolved specific variants in genes associated with lipid processing and cholesterol management that allow it to consume a diet that is approximately 50% fat without accumulating the arterial plaque deposits that would be fatal in other species. This specific metabolic adaptation is one of the more medically interesting aspects of polar bear genetics, with some researchers investigating whether the underlying genetic variants might provide insights into human cardiovascular disease. The hybridization between polar bears and brown bears that is encoded in their shared genomic history has taken on new relevance in the context of recent observations of hybrid animals in the wild. In 2006, a hunter in the Canadian Arctic shot an animal that was subsequently confirmed by genetic testing to be a first-generation hybrid of a polar bear mother and a grizzly bear father, and subsequent genetic analysis of the populations in that area has found evidence of multiple generations of hybridization. These hybrid animals, colloquially called growler bears or pizzly bears, are not merely genetic curiosities. Their occurrence reflects the ecological reality of polar bear and grizzly bear ranges, overlapping as grizzly bears expand northward into areas where receding sea ice and changing vegetation are creating new habitat for them, and as polar bears spend more time onshore in areas where grizzly bears live. Whether these hybrids represent a meaningful evolutionary pathway for the polar bear's genetic legacy under climate change, or whether they are an ecological edge effect of limited long-term significance, is one of the more genuinely open questions in Arctic wildlife biology. The polar bear has survived the glacial cycles of the Pleistocene, the dramatic climate oscillations that repeatedly expanded and contracted the sea ice habitat that the species depends on. It survived the warming periods between glaciations when sea ice was reduced, retreating to ice refugia in the high Arctic, while the lower latitude parts of its range became temporarily inhospitable. It has demonstrated, across hundreds of thousands of years of geological time, a resilience to climate variability that offers some grounds for cautious optimism. But the caution is necessary. The current warming trajectory is faster than the rate of warming at any point in the Pleistocene record, and the global integration of the modern climate system means that there are no refugia to retreat to if the warming continues at its current pace. The ice of the high Arctic, where the polar bear has historically found shelter during warm periods, is warming faster than any other part of the planet. The geological precedent of survival through past climate change is genuinely meaningful, but it does not translate straightforwardly to the current situation, which differs from past warmings in both rate and the absence of refugia. And so the polar bear walks on, out there in the dark, on ice that is thinner in some places than it used to be, and absent in others where it once reliably formed, in an Arctic that is warming at more than twice the global average rate, and that is, by every physical measure available, changing faster than the bear's extraordinary biology has ever been asked to accommodate. The bear does not know this. It knows ice and seal and cold and the smell of the wind, and it moves through its world with the unhurried competence of an animal built for exactly this. Here, now, in the winter dark, its feet read the ice, its nose reads the wind, its fat stores carry the summer's hunting into the winter's fast. Its cubs are warm against its side in the den, growing toward the ice they have never seen, dreaming, if bears dream, of the cold white world waiting for them when the snow melts from the entrance and the light comes flooding in. The Arctic night is quiet around you now. The wind has settled, or perhaps you have drifted far enough from it that you can no longer hear it. Somewhere out on the ice, the white bear is still moving, unhurried, reading everything the cold air has to tell it, carrying all that insulation and all that fat and all that millions of years refined patience across a surface that holds it up, for now, as it always has. You have been tonight inside the hollow shaft of a polar bear hair, inside the den where the smallest possible beginning grows into something that will walk out onto the ice and survive everything it finds there. You have been inside the nose that smells a seal through a meter of snow, inside the paws that read the ice like a language, inside the blood that runs warm through temperatures that should not be possible for warm blood. The polar bear carries all of this quietly, as it carries everything, without drama, without complaint, in the long, patient rhythm of a life built entirely around the cold. Let the warmth of this room feel like something earned now, something the polar bear would understand. The warmth that matters most in contrast to what lies just outside it. Your breathing is slow. The night is deep, and out on the ice, the bear has found what it was looking for and settled, and the Arctic dark has closed around it, white on white, still and complete and perfectly at home. Good night.